Okay, so I guess let's start again. So thanks everybody for coming. I'll be presenting C-2PO, which is a weakly relational pointer domain. This is mostly the work of Rebecca Ghidini, who's a master student of ours who sadly couldn't be here, and also together with Julian, Erhard, and Helmut Seidl. So let's maybe quickly take a look at numerical abstract domains. And there an observation that has been made for a long time is that you have basically extremes along this axis of precision, of very precise but sort of slow. And on the other hand, you have not very precise but very scalable. And for example, on this axis, people often see intervals and polyhedra as the extremes. And then sometimes in the early 2000s, a compromise was proposed there by Antoine Minet and others. And the key insight there was, okay, maybe I don't need to be fully relational, maybe I give up some of the precision, but then I still get something that is relational, but also scales meaningfully. And since then, a whole zoo of other weakly relational domains has been proposed, and generally there has been a lot of success there. And at some point we started wondering, okay, but why has this only been done for numerical domains so far? So we started wondering, maybe you can apply the same principle also where you only check pairs of the relationships between pairs of variables also to other domains. And our first paper in this line of work was some general construction to turn a relational domain into a weakly relational domain by some approximation. And we considered, for example, two disjunctive constants and also considered a little bit domains that track strings or in general conjunctions of inequalities between lattices. But then the other question also arose, okay, so for these you can do it, but what about, for example, the heap in C programs? So what about pointers in C-like languages? And there you also have this situation where you have techniques that are quite fast, but also very coarse. So if you think about tracking points to sets, potentially even flow and context insensitively, this tends to be very fast, but also very coarse. And on the other hand, you have techniques that are very precise and can give you very detailed information such as shape analysis or things that are based on separation logic. However, there you also have to pay the price of this precision. So we started wondering whether we can maybe come up with some sort of compromise, and the compromise that we are proposing here is actually not C-3PO, but C-2PO. So the question is, why C-2PO? And the idea here is that we have some earlier work on something that is called the two-pointer logic, and we were wondering whether one can turn this two-pointer logic into an abstract domain for C. And so it's the C plus the two-pointer logic. What we have in this two-pointer logic in general are conjunctions of mostly equalities between pointer expressions where you have at most two variables in each of these equations. So what we did in this paper was we provided efficient approximation and implementation and experiments. And also we have extended this two-pointer logic with support for malloc, because in C you cannot do without dynamic memory allocation. And then the other thing that we found to be very important to add was some notion of disequality between memory blocks. So I'll go into that in a bit. Let's maybe first look at the two-pointer logic. So what might the formula there look like? So we have some formula here that has some equalities between pointer expressions. And in these equalities between pointer expressions, you can also have dereferences and you can have offsets. So you see this here. So one type of information you can have. The other thing you can have is you can have disequalities. So here you would say, okay, Z is definitely different from the address of Y. And there also you can have in the disequalities, you can have dereferences and offsets once again. And then the last thing that we have added here are, as we've talked about, these disequalities between memory blocks. So this here would say that if you evaluate Y at 5 and dereference it, then you will be in a different block than the block that X is in. So a little bit more formal. What does this logic look like? Well, for the terms, you have, first of all, the address constants. Then we allow ourselves a set of registers. So basically, you can think of these as any sort of variable in C that never has its address taken. So it cannot be modified by some assignment to some place. We can directly see when it's modified because it's only modified directly. And then we also allow dereferencing. And there we allow some arbitrary offset C for dereferencing. Then we have some writing conventions that make it easier to write things. So if we dereference something at an offset of 0, then we just leave out the offset, makes it nicer to write it down. And also for variables, if we dereference the address of the variable X, we just write X. That just makes the formulas a little easier to understand. Then our atomic propositions, they look like this. So you either have equalities between terms with an offset, or you have disequalities between terms, once again with an offset. And then lastly, what's new in this work here are these block disequalities. And the idea behind block disequalities is the following. If you have standard compliant C, then you can do address arithmetic, but you can never leave what the C standard calls an object with this address arithmetic. So if you have a variable x and a variable y, you cannot use address arithmetic to go between the two of them. Because basically you need to always stay within the same block. And then one of these block disequalities basically says, okay, there is no offset z such that you can add it and go from one to the other. And then our formulas are simply conjunctions of these atomic propositions that we've seen. Now for the equalities and disequalities, I guess it's sort of easy to imagine where they come from. For the block disequalities, it's maybe useful to say once again that for all variables, we have the block disequalities. And also when we do a malloc, C guarantees us that we basically get a fresh block of memory. So we can also say that all of the mallocs, all of the blocks that we have allocated will be in different blocks. Now with these equalities, what happens is if you have a bunch of equalities, you basically get other equalities from them. So if you have two equalities, you get potentially a third and potentially many more. So for example, if you know that x is equal to y, and you know that y is equal to this dereference expression here, then you can infer, okay, x is actually equal to this longer expression here. And you have the same situation with equalities and disequalities. So if you have an equality and a disequality, then you can also infer, basically here in this case, that x is also not equal to this longer expression here. And you have a lot of these inference rules where basically a lot of equalities and disequalities are implied. And it is even so that usually you have infinitely many equalities that are implied. So for example, if you have an equality that x equals y, then you can keep dereferencing on either side, and this is still an equality that will be implied. So what we need actually is a nice and compact way to represent all of this information. And there our proposal is to, instead of directly considering these formulas, we consider something that we call a kernel representation, which is this nice 5-tuple here. So I will explain what we have here. So first we have a set of terms that we are talking about in this abstract value. And here this is a set of terms is supposed to be subterm closed, and it is supposed to contain at least all of the terms that our original formula psi also had here. Then for the equalities, we represent it with something that we call the quantitative congruence closure. So you have this pi and the omega, and this is a compact representation of the equalities. We'll see how exactly it works in a second. And then for the block disequalities, we now only store block disequalities between the representatives of the classes in this congruence closure, and we also do the same for this normal disequalities. Now this quantitative congruence closure, what do we mean? Well, we mean a congruence closure, but the elements that you have in there that are equivalent to each other, it means that they basically can be reached with a constant offset. And then what you have obtained is you have obtained a representation that is unique for a given set of terms, provided that you have fixed some total order on the terms such that you can always pick the smallest term as the representative. So what does this look like? Let's consider some formula psi here, and I have marked the equality in orange. And we have picked the set of terms to be the address of x, the address of y, our temporary a, and x and y. And then in pi, we basically have the different congruence classes. So the address of x and the address of y are in their own thing, the same for y. However, a and x are put into the same class because we have here that there's a constant offset between a and x, namely this offset 2. And then in the omega, for all of the elements in each of the classes, we basically write down what is the offset from the representative. For the single element ones, this is very easy, it's always 0. And then here for this x, the offset is 2, because in our term order we have decided that these auxiliaries are smaller than the variables. So this is our quantitative congruence closure, and we have implemented this with a quantitative version of the union find data structure, and you can find more details on this in the paper if you're interested. Now for this formula we have talked about how we represent the equalities. However, there's still the disequalities to go. So what do we do for disequalities to get the complete kernel representation? Well, block disequalities, we don't have any, so this is easy. And then the disequalities, we once again store them only about the representatives of the congruence classes. And here A happens to be the representative and Y is also the representative. So we can just store it as this 3-tuple here. Okay, so now we have how we represent our abstract values. The next question is we need to define the lattice operations on those. And the first one that we give here is the meet operation. And there you say if you have a two non-bottom abstract values, K1 and K2, then to define the meet, we first extend the set of terms for both such that they are equal. And then we step by step add the propositions from K2 into this abstract value for K1. And this is a convenient way to define it because we already need to provide transfer functions for all of the guards anyway later on, and so basically we can do the meet here in terms of adding single propositions. Then what does the partial order look like? Well, for our partial order here we make use of the meet that we have just defined, and we say that K1 is smaller or equal to K2 if and only if meeting K1 and K2 together gives you K1 again. So this equivalence that we have defined here, or if two values are equivalent according to this order, then this implies the semantic equivalence. However, it is not precise, so the other way around does not hold. So if two kernels K1 and K2 are semantically equivalent, but one of them talks about a larger set of terms, then the one that talks about the larger set of terms would be truly smaller than the other one. So this is a drawback that we have here with this definition of the partial order. Then the next question is, what do we do for joins? And if we were in the formula world, everything would be very easy. Because in the formula world, you just say, okay, the join is the OR. However, the OR is sadly not in our class of formulas. So then the next idea would be, okay, how about I consider all implied equalities? However, there's also a result by Gulvani, Tivari, and Nekula from 20 years ago that it is not always possible to represent all of these implied equalities as a finite conjunction. So this is also a problem. However, here we have nicely sidestepped this problem because we are not talking about the formulas, but we are talking about our kernels. And for our kernels, we have a fixed set of terms that we talk about. And so this is no longer an issue here. And we simply consider only the intersection of the terms. And then for the equalities, the join actually is the least upper bound that we have here. And for block disequalities, we need to do a little bit of work because after the join, some equivalence classes may be split and the representative may change. But there I would also point you to the paper for details. Now for the join, we have only talked about the equalities. Now what about the disequalities? Actually, there we once again have a bit of a problem. Namely, if we consider two formulas, psi 1 and psi 2 here, and one time we have A is equal to 2 plus X, and the other time we have A is equal to 3 plus X, then both actually imply that A is unequal to Z plus X for any Z that is not 2 or 3. So basically, we have now here obtained a cofinite set of disequalities between A and X. And there, once again, we have this problem that we do not have a best finite abstraction for it. So what we do, or what we have to admit, sadly, is in the presence of the disequalities, our join actually remains an over-approximation. The advantage of the definition that we have done for the join is that actually in this setting, if you apply the join repeatedly, then your sequence of values will become ultimately stable. So basically, we can use our join as a widening. And still, when we are not widening, if you want to get some of the precision back, what we can do is we can basically grow the term sets of the argument to the join before we apply the join. So what this means is that the values, the concretization remains the same if you grow the term set for one of these things, but the abstract value becomes smaller in the lattice order. So if you are careful, you can basically do this to avoid being too imprecise when you do the joins. And yeah, you can preserve some additional information. The other question, we've talked about widening, so immediately the question arises, okay, what about narrowing? And actually here we have the situation that we have infinite descending chains of kernels. So we need to do some engineering. And basically here the solution is we somehow need to bound the magnitude of the appearing constants. And for the details there, I would once again direct you towards the paper. Okay, so we have defined our lattice, we have defined the operation on it, so now we actually want to do some assignments with it. And first of all, let's consider what we do when we have an assignment to an unknown expression. For example, we assign T1 to question mark, and then what you need to do is you need to forget the information about all terms that may be modified, and that is all terms that may have the same address as T1. If T1 is an atom, then it is as an auxiliary, then it's not really a problem, because you know that nothing has the same address as this auxiliary. You can simply remove all formulas that basically talk about A, and then you're done. If it's actually an expression where a pointer dereference happens, then the situation is a lot more complicated, because then you can keep only equalities or disequalities about the terms where you can actually prove that these two things will never be the same. And this can either be the case because you know from the normal disequalities that it will never be the same, or you know that the things are in two different blocks and they can also never be the same. And in these cases, it is basically crucial to know that these memory cells are not the memory cells that the write is actually looking for. What we can do when we implement this in the static analyzer, though, we can do a little bit of a Jedi mind trick. Namely, we can additionally also use some information that maybe a non-relational heap analysis has computed and provide this as an additional input to this transfer function to say, okay, you do not have the block disequalities or normal disequalities for these two things, but we can assure you that they will never be equal. Now, when we assign something a bit more difficult, a bit more complicated, then the general procedure is very similar. We only make use of these auxiliaries here to make our lives a little bit easier. So basically, we add a fresh auxiliary, then we add an equality between the right-hand side and the auxiliary, then we remove all of the terms that are potentially modified by the assignment, as we have seen before, then we add an equality back, and then lastly, we remove the auxiliary again. This is a little bit of a trick to make it easier. Okay, then I promised I would talk a little bit about dynamic memory allocation. So what do we do if we have something like this? So we have T1 is equal to call to malloc. Well, first of all, everything that potentially modified by this assignment needs to be removed, as we did before. And then for all of the terms that are appearing anywhere in our equalities, disequalities, everything, we can basically add this new block, disequality, that the block of all of these things will be different from the block that we have just newly allocated. Because intuitively, nothing will be in the same block that we just got from malloc. All right, so we have actually also implemented this domain within Goblint, which is an abstract interpreter for real-world multi-threaded C programs based on side-effecting constraint systems. And we have experimented to get a feeling of the precision of the domain. We have experimented with the coreutil programs. And what we did is we basically generated invariants with C-2PO and then instrumented the programs with these invariants. And then we compare three different configurations of this Goblint tool. Namely, we consider a basic configuration where we only have a non-relational pointer analysis. Then we consider a var-eq analysis, which tracks more general must-equalities. And then we considered our C-2PO domain. So in total, we generated about 20,000 assertions for these programs. And luckily, C-2PO was able to verify its own assertions. Everything else would have been depressing. But what's also interesting is this other relational analysis, var-eq, was only able to show about 8,000 of these assertions. And if you go to a non-relational analysis, then it's only about a fifth of the things that can be shown. So this seems to be some evidence that the C-2PO domain actually computes some interesting invariants that are out of reach for these non-relational analysis. Now the other thing always is, well, how does it perform this entire thing? For this, we have considered a larger set of benchmarks. Namely, we have considered all of the soft verification competition, the reachability category, and we have basically plotted the runtime of this base, so this is this non-relational analysis, versus the runtime of the C-2PO. And you see the runtime of base on the x-axis and the runtime of C-2PO on the y-axis. And basically what this means is for all of the data points that are below this diagonal base was slower, and for all of them that are above the diagonal, C-2PO was slower. So we can see that in general, we actually observe a little bit of a slowdown, but it seems the slowdown is not too bad. So it's usually below a factor of 3. So this is the 95th percentile value. And we consider this to be quite good, to have a slowdown of 3, but being somewhat relational. And then there's also these cases where we're actually faster, and this may be because we have basically identified key parts of the program that are actually not reached by being relational, and then sometimes being more precise can even be faster. The other thing that's maybe a bit sad that we have to say here, it did not significantly change the number of correct verdicts on these SVCOM tasks. So these tasks, they come annotated with some goal that is to be proven, and often this is quite an intricate goal, and apparently we got more precise, but quite often we're still not precise enough to prove this invariant that the SVCOM wanted proven. All right, so to quickly wrap up what we have done, we have proposed this novel domain C-2PO to track equalities and disequalities between pairs of pointer expressions. We have seen that the block disequalities are crucial for handling assignments, and we have also done some preliminary experiments in Goblint that look sort of promising. And with this, I'd like to thank you for your attention, and I look forward to your questions.
So, anybody has got a question for Michael? Yeah.
What do you do in situations where a pointer might point to two different mallocs, maybe as a result of a merge or join?
So if the pointer may point to two different mallocs, then you sometimes need to get rid of the block disequalities. Then you cannot maintain them anymore. But it's something that can happen and happens quite regularly. If you think about some sort of branching and then you join again, then it may be two different mallocs, yeah.
Okay. You?
Yeah, so I have a question about the disequalities and how you represent the set of all disequalities. Because when you allocate a fresh block using malloc,
yep,
then you become different from all the other blocks.
Yes.
So do you represent all the disequalities one by one, or do you have a set of mutually exclusive set like you do in separation logic to have a shorter version of?
So those we don't actually represent explicitly. So the Goblint analyzer for these malloc blocks, basically it creates new variables, and then we basically have this implicit information that the blocks for variables are always disjoint.
So you have names for different IDs, and if the different IDs for different blocks, and if the IDs are different, then
yeah,
okay.
Yeah.
Thanks.
So it's only for unified presentation here, because otherwise you get into these problems of how to best represent it, and that this was the easy way out. Let's put it like this.
Okay. More questions? So you said that you were not quite there with respect to the SVComp benchmarks. Would C-3PO help you?
I mean, C-3PO is very smart, so maybe yes. Realistically, the problem of some of these tasks is that they come from the model checking community. So they are sometimes annotated with invariants that are very hard for abstract interpreters to prove. So you would need to do a lot of loop unrolling and such things. Right. So I don't know if C-3PO might help solve more things, but I don't think.
I mean, would it make sense to have 3PO with the pointer?
Okay. Yes.
Yeah, no, I'm not.
Whether having 3 pointers would actually help.
Yeah,
I'm not.
Would that make any sense? I'm not sure that it would.
So I think it might be interesting to do it, because a situation where you might actually want to have 3 pointers is if you think about offsets into arrays, for example. So then you could have, okay, I have an equality between some variable and then the kth element of this array. And then you would have a 3-pointer expression. Whether this would go a long way towards the SVComp task, I cannot say. But in general, it might be an interesting generalization of this thing here.
Yeah. Other questions? Otherwise, thank you.
Thanks.